Okay, so now what we're going to be doing is we're going to try to find the derivative of an exponential function in the form of y is equal to b to the x. Just like we've been doing with everything, we're going to go back to the beginning and we're first going to find the derivative of b to the x using first principles, so using limits. So if my original function is f of x is equal to b to the x, and I want to find the derivative, so f prime of x of b to the x, what I'm going to do is I'm going to take the limit, going back to first principles, as h approaches 0 of f of x plus h minus f of x all over h. So this is going to be equal to. So within my function, I'm going to replace x with x plus h. So I'm going to have the limit as h approaches 0 of b to the x plus h minus my function, and my function is b to the x, all over h. Now, if we put in 0 here, we're going to have 0 over 0, which is indeterminate. So we need to try to manipulate this equation slightly. Before we do that, I want to talk about something, just an aside, from Math 10C. And then it might help you see where we're going to go with this. So from Math 10C, if I said to you, so you could just jot this down as a little aside, a to the m times a to the n. So using exponent laws, when bases are the same and the bases are being multiplied together, we know that we add the exponents. So that's going to be a to the m plus n. If I give students this, though, and I say, okay, a to the m plus n, break that apart, well, we could break that apart by saying, okay, that would be a to the m times a to the n, right? So this and getting an answer of a to the m plus n, you've seen that, and everybody's really comfortable with that. But if I start here, a lot of students have a hard time saying, oh yeah, I could separate that by writing a to the m times a to the n, because this could be combined by just adding my exponents. So the reason why I show you that is because we could break this apart. B to the x plus h is the same as b to the x times b to the h. So let's rewrite that. This would be the limit as h approaches 0 of b to the x times b to the h, right? Because this could be combined to be b to the x plus h. Then I have minus b to the x all over h. Now if you look at this denominator and I say, okay, well, what can we do with this denominator? Hopefully you see that you could factor out a b to the x. So that will give us the limit as h approaches 0. Let's factor out a b to the x, and we'll have b to the h minus 1 all over h. Okay, so what's happening is our limit is going to be as h approaches 0. Now, this is going to give me an issue here, right? Because I have the 0 is being affected by the h is being affected by the 0. But this part of the limit isn't being affected by as h approaches 0. So what I could do is I could actually pull that out. And I could say, okay, this is going to be equal to b to the x I could pull out, because that's like as h approaches 0, that's going to affect this portion of the limit. So pull out this b to the x, and then I have the limit as h approaches 0 of b to the h minus 1 all over h. So I've just taken the limit by first principles. The limit is giving me the derivative of the function. And what I sort of want you to see, it looks complex and you're like, okay, well, what am I really looking at here? We're trying to take the derivative of b to the x, and we did take the derivative of b to the x. And what we got is the derivative of b to the x is b to the x. So when we have an exponential function, b to the x, and we take the derivative of that, the derivative is actually itself multiplied by this limit here. And this part is sort of going to scare students, but I'll sort of show you what's going to happen with this. So the derivative of b to the x is b to the x multiplied by this value here. Okay, so what's happening over here? This portion is going to be unique for every value of b. So this is going to be a calculable number depending on what the base is. We're going to get a different number if the base is 2 versus if the base is 3 versus if the base is 4. So this portion of our limit is unique for every value of b. This is going to give us a constant. It's going to give us a number, a calculable number, something that we could calculate. Essentially, what we have now is the derivative of b to the x is going to be b to the x. So the derivative of an exponential function is itself, so the derivative of b to the x is b to the x multiplied by whatever value we get this limit to be, and it's essentially that value is going to be a vertical stretch factor. So multiplied by a vertical stretch factor. Okay, so this value is going to change for every value of b. So I'm going to show you a couple different examples, and then I'm going to show you how we're going to sort of simplify everything. So let's just say I said, I want you to find the derivative of 2 to the power of x. So my base is 2. The derivative of 2 to the power of x is going to be 2 to the power of x. The derivative of an exponential function is the exponential function. And then what I need to do is I need to multiply that by the limit as h approaches 0 of b to the h, so b is 2, 2 to the h minus 1, all over h. Now, in order to calculate what this value is, what I could do is I could take values really, really close to 0, right? So I could take h as 0.1 or 0.01, 0.001, and I could find out what this limit is. So if my base is 2, I'll just tell you. So here's the values here if your base is 2. But if your base is 2, what that portion of the limit is going to approach is it's going to approach 0.69. Okay, so the derivative of 2 to the x is 2 to the x multiplied by this stretch factor here. So far, again, don't worry about this number just yet. Let's do another one. Let's change our base to 3. So write down y is equal to 3 to the power of x. If I say I want you to differentiate 3 to the power of x, what's the derivative of 3 to the power of x? Well, the derivative of an exponential function is itself multiplied by the limit as h approaches 0 of b to the h minus 1, so the base is 3, to the power of h minus 1, all over h. Again, I can't plug in 0 because I would have 0 over 0. So numerically, I would pick values really, really close to 0. I'd pick 0.1, 0.01, 0.001, and I would say, okay, well, what is this limit approaching? And what this limit is approaching, it's going to get really close to 1.1. So the derivative of 3 to the x is going to be y prime, is going to be the derivative is the exponential function itself multiplied by whatever numerical value we get over here for whatever base we're using. So this is going to be approximately 1.1. Okay, so what do you what are you trying to get from this? So the most important thing to get is the derivative of an exponential function is the exponential function itself multiplied by, and then we've got this number that we have to contend with. Now, what I sort of want you to see is that we have a base of 2 and we get 0.69. We have a base of 3 and we get 1.1. Ideally, I would like to not have to deal with this limit here, right? And how I could do that is there a base between 2 and 3 that if I plugged that value in, I would get a 1 here? So that's kind of like what mathematicians looked at. Is there a number between 2 and 3 that if I plugged in that base, the limit would approach 1? And then I wouldn't have to contend with this portion of the limit. And the answer is yes. So there is a value in math where if we plugged that value in, and this would be the base here, then that portion of the limit would go to 1. Now, the person who discovered the number, his name was Leonhard Euler. It looks like Euler, pronounced Leonhard Euler. And it's an irrational number, and this number is called e. So if we have an exponential function, y is equal to e to the power of x, what happens is if I said I want you to take the derivative of this, what we would get is we'd get y prime is equal to the derivative of an exponential function is an exponential function multiplied by the limit as h approaches 0 of e to the h minus 1 all over h. This, though, when your base is e, this is just 1. So what that means is the derivative of e to the x is e to the x. So a couple of things. I don't want you to freak out when you're seeing e to the x. E is a number, okay, it's an irrational number, and it would be like saying y is equal to 2.71 to the power of x. If I said I want you to graph this, if I want you to graph y is equal to e to the x, the base is a number greater than 1, so it's going to be a growth function. The a value is a 1, which tells you that the y-intercept is 1. This would be the graph of y is equal to e to the x. Okay, it's just the base is this 2.71. Irrational though, so it would keep going on and on and on. Okay, so again, I'm sort of saying it a lot, but to hammer in this point, if your equation or your function is e to the x, and I say, what is the derivative of e to the x? The derivative of e to the x is e to the x. It is itself. Another way I could write this is I could say I want you to differentiate e to the x with respect to x, and the derivative of e to the x is e to the x. Now, what we're going to see in the next video is what happens if I change x to, let's say, 5x. So let's say I want you to differentiate with respect to x, e to the 5x. The derivative of e to the 5x is e to the 5x. It's the derivative is the function itself. And then we're going to multiply it by whatever the derivative of 5x would be, and that's going to be 5. So the derivative of e to the 5x is 5e to the 5x. Okay, I'll show you one more. If I gave you, I want you to differentiate with respect to x, e to the power of x to the 4. The derivative of e to the x to the 4 is the function itself. So e to the x to the 4. And then you're going to multiply that by the derivative of x to the 4. So according to the power rule, it would be 4x cubed. And that would be the derivative of e to the power of x to the 4.